Welcome back, everyone. I hope you enjoyed the short break we had between these two speeches. It is my pleasure to introduce to you now two gentlemen who are working for ING Romania, Mr. Alexandru Nedelcu and Mr. Mihai Simu. They are both development engineers for ING Romania. Alexandru loves open source. He is the author of Monix and a contributor to Cat's Effect and to other libraries from type-level Scala ecosystem. Also, he is writing on alexn.org. Alexandru, I hope I didn't make any mistake here. Mihai is a backend developer who has been working with Scala and functional programming for the better part of his last 6 years of career, both in startup community and within ING, interested in correctness by design, building fast, reliable and scalable backend systems. They will speak about, oh no, I won't tell you what they are going to speak about because it is them who will tell you the subject of their presentation. Please, your virtual applauses for Alexandru and Mihai.
Hey everybody. I hope you can see my screen. This is Alex, and alongside my colleague Mihai, today we are going to talk about functional programming in Scala at ING. So we are Vesper being the code name. That logo right there was created by a colleague of ours who was also passionate about, the more creative stuff. And it references Lambda Calculus and ING. We are inside ING, we are Romania's payment engine, and we have ambitions for more. We are in production, which and already heavily refactored. And we've got superpowers that we want to talk about today. So we are a distributed team working remotely. We've got great people from Cluj, Timișoara, Iași, Bucharest, and we are growing. And we started with a remote culture ever since the beginning of the project. I believe that our tools help us be distributed and remote, which is why I'm mentioning this. We are building on top of Scala and running on top of the JVM. Noteworthy maybe, as from what I know, .NET kind of dominates banking in Romania, and I hope this will be the start of Scala's hegemony. And we practice functional programming, actual functional programming, and we'll talk about that in a few moments. And I also seen mentioned at this presentation, but we also use technologies that you may have heard of, such as Akka Stream, Akka Cluster, to model event sourcing, although we don't really use or like the actual actor model. We stay away from that, actually. And we, as non-functional requirements, we are building reusable components. Our project is actually split into multiple sub-projects that are built as libraries meant to be published internally and maybe even externally. So we have a very library-oriented mindset. Also, many backend projects want resiliency, consistency, horizontal scalability. We think we can actually achieve that. But let's talk about functional programming, which is one of our superpowers. FP is an overloaded term in this industry. It's not about higher order functions. It's not about passing around functions as values. Although it's also about that, but not really. Functional programming is programming with mathematical functions. Mathematical functions are simple mappings between a domain and a codomain. In our programming languages, we are talking about data types or classes in Java. And these mappings, it's noteworthy to mention and required, these mappings are unique, meaning that for any input parameter, the function always returns the same result. And this scary looking definition right here, I think I saw it in my 9th grade, or maybe it was elementary school, but all it expresses is that functions are not non-deterministic. So for any input, for every input, you always get the same result. Math can be scary, but it really expresses simple things. So it's programming with mathematical functions. It's not about procedures. It's not about subroutines like an assembly, aka pure functions or functions without side effects. Or alternatively, we can talk about programming with values because once you have values, you are in essence talking about pure functions. So that means primitives and immutable data structures. And an important property of functional programming would be referential transparency. An expression is referentially transparent. This is the textbook definition. If it can be replaced with its corresponding value and vice versa without changing the program's behavior, meaning that you can take any function call and replace it with its result without changing the program's behavior. And this is like a really useful test to see if a function is pure or not. So in case we have a function called foo, if we invoke it twice, or if we invoke it once and then reuse the same result, so invocation with the same parameter, let's say, in both cases, if the function is pure, the program behaves the same. If the function is not pure, meaning that it launches rockets to Mars, maybe, in the first case, it would launch those rockets twice. In the second case, it would only launch them once. It goes without saying that the programs are not equivalent. So if the function call is referentially transparent in this case, then the function is pure. So this is like the test you need to do because frankly, sometimes it's really hard to see if a function is pure or not. And this happens also, this happens naturally in our day-to-day programming without us even realizing it. So let's take, for example, this login base2 function based on Scala's natural log function. So the right-hand side of this expression could be cached in an intermediate globally accessible constant. So we could have something like this, like a constant where that part of the expression is already calculated. And we can do this because the natural log function in Scala is pure and not side effecting. If it would launch rockets to Mars, we would not get the same behavior. Now, I believe you came here because you want to hear of industrial usage of functional programming. So here is an actual example from our own code. This is a component from our code that models a message queue that can delay messages, that can schedule messages to be triggered at a certain time, say tomorrow at 8 o'clock. This is a component that is a pure interface, described as a pure interface. A trait is called in Scala. It's an OOP interface. We love object-oriented programming actually, as it's complementary to FP. So we have an offer method for registering messages and a try poll that queries the database for messages to be processed. We currently implement it with a relational database, but it accepts, the interface is generic enough, it accepts any data store actually. But here's how the method looks in our actual code. I hope you can see this code, although if you don't understand it fully, no worries. Try-poll is a value here, returning an IO data type. It can be a value as IO is like a pure future or like a JavaScript promise, except it is lazy and referentially transparent. It's like a function with no parameters that hasn't been executed yet. This is one of the reasons to use Scala because it has a really good IO implementation, by the way. So this implementation is based on relational databases and it composes 3 atomic database operations in a single one based on the compare and swap pattern that you may have seen in Java's atomic reference. No atomic references here, but the same principles apply. So we get the current timestamp, which is a side effect. But it's modeled as a side effect, as a pure function here. We also get the first available message to be processed that expired, right? In case there are none, we return. In case there are some, and notice use here of union types. In case we have a message, then we try acquiring the lock for it by updating the table. In case the update fails, it means we have a concurrent process doing the same thing, so we retry. This is a recursive call. And in case it succeeds, we deserialize the payload. And then here we also compose an acknowledgement method. That's the release of that lock that we need in order to get rid of messages once they are processed. And in case the release never happens, then there's a timeout happening implicit in this acquire table method here. So this is like a simple expression. This is like an expression, right? That composes 3 atomic operations into a single atomic operation. This is how actual FP code looks like in practice. And this code is suspending side effects as well, doing real things, right? So we love Scala because it has a really static type system. We describe more things at compile time. There are no Spring annotations in our code, almost no Java agents or runtime reflection, our programs get validated mostly at compile time. We reject Spring on principle, and if there are Java misfits amongst you, you may want to do more at compile time, then Scala's culture is for you. Scala also has a culture oriented towards FP. Culture is important. Java is perfectly capable of being used for FP, but in practice it doesn't get used, as doing this is swimming against the tide. And it's an optimal language for FP because it's expression-based, it has union types. In fairness, Java 17 also has union types, tagged ones, but Scala 3 also has untagged union types, like in TypeScript, which work great with object-oriented programming, actually. And Scala also has higher conduct types and type classes. And I'm sorry that I don't have time for these features, by the way, because this is what makes Scala unique. This is what makes Scala expressive at expressing things that more things at compile time. It's unique on top of the JVM. No other language goes in that direction. It's not just a Java++. And we also have access to the type level ecosystem, an awesome ecosystem of libraries that we can use. We collaborate with type level contributors. And when we need help, we can usually get it. For the business side, in practice, for us, this means reduced defects rate. And in computer science, unfortunately, there isn't a lot of science done, but the few studies that we have available suggest that indeed static typing and functional programming do reduce the defects rate in production. For us, it means easier maintenance, tests, refactoring. We get tests for free, basically, and we have a really strong refactoring culture, fearless refactoring, because the compiler helps us avoid accidental complexity. And we can talk about local reasoning due to functional programming, meaning that we have an easier time divorcing functions from their surrounding context. We have mathematical rigor when we talk about FP design patterns. Design patterns in general can be confusing, but FP design patterns are many times described via math. And math is scary, but math is precise. And now you don't need to know category theory, by the way. And we are hiring great people. This is a contention point. People complain that they can't find Scala developers. Well, sure, but the Scala developers you can find are pretty good, actually. And it's equally hard to find good Java.NET developers. And if you find good developers, they can be retrained in weeks. Functional programming or not, it's still the JVM and its ecosystem. We are still learning. I'm still not bored. And this is coming from a guy that used to jump programming languages. And it's fun. I mean, oh my God, folks, do you remember the time you used to learn programming and it was actually fun? That's how Scala and functional programming feels like. Now, we are building a payment engine, so let's see how the application looks like at a higher level. I will let Mihai describe our architecture and also introduce another superpower, which is data flow programming.
Okay. Thank you, Alex. I am going to share my screen. Second, share screen, share screen. Okay, Alex, can you please confirm that you see my screen?
I see some screen, I'm not sure. I think it's still mine.
Okay, okay, 1 second. How about now?
Let me stop my screen. Try again.
Yeah, it says that it's sharing my screen. Okay, you can see it. Okay, so I'm gonna just pick up where you left off. Okay, hi everyone. I'm going to expand on some of the points that Alex made regarding functional programming and give you a concrete application of how we use this thing inside ING. So the first thing that needs to be said is that a technological ecosystem is only as good as the stuff that you can build with it. So it's very important how we use it. And in our case, we build payment processing engines. We process transactions. In a very simplified version of things, this is a schematic view of it. We take things from an input source, from an input queue. We run them through a processing step where we debit and credit the involved accounts, and then we send them on their way to a destination queue, to a destination transaction sink, where they are marked as finished. There's an important step in between processing and sending it to the destination. There's a deletion step where we actually delete from the input queue so that the transaction is no longer inside the input and we can pick up with the other ones. This is a very simplified version of things, and in practice, it's much more complicated than that. So I wrote up a few example requirements for the purpose of this presentation to see the kind of concerns that we deal with in practice. So we usually, you receive things as strings. Normally, you would receive things as simple strings, which you need to parse. You need to transform them to an internal banking format. There are many banking representations for transactions with XML or whatever, and you need to make sure you respect those standards. After you've parsed them to an internal format, you might want to do fraud detection to verify that your transaction is not fraudulent. And if it's fraudulent, obviously reject it. Another concern we have is that some transactions can only be processed during certain time windows. Some may have 24/7 processing, and some might have specific timeframes, and only during those timeframes you are allowed to process them, not outside. If they come in outside of those timeframes, you need to store them and pick up the processing at a later time in a few hours or something. We need to delete from the input queue when we are done with all of this. Like I said, we have a step to remove transactions from the input queue. And at the end, we need to make sure that we process them at most once. Errors can occur all along the way in this thing, and you need to account for them. You need to make sure you handle them correctly. Okay, so how would we build this? What is the logical diagram of this? And it looks something like this. This is the logical diagram, the logical translations of some of these example requirements which I gave. Transactions come in from a source. They come in as a string. Let me actually point here. Laser pointer. Okay, so they come in from a source. You go through a parsing stage where you translate them into an internal format, and then you do fraud detection. In case the transaction is marked as fraudulent, you push it to a reject step where you don't actually execute it, and then all the way to the output. If it's not fraudulent, if it's a valid transaction, you verify if you are during the working hours where you're allowed to actually process it. If you are, you go ahead and process it. If you're not during the working hours, you want to push it to a so-called delayed store. This is an intermediary storage that you have, and you pick it up a few hours later where you run it again through fraud detection. So simple translation of these requirements, like parsing, fraud detection, and this verification for working hours are probably the most interesting steps we do here. Now, the question is, how would we translate this into actual code, into actual Scala code? And I'm getting back to Scala. I'm getting back to the programming language. The initial approach would be to just use function. This is the most intuitive, straightforward way we usually do things in functional programming. We take each of these steps and write a function for it. And these functions can get to be arbitrarily complex. It doesn't matter. The point is, this is the main abstraction that we would use as an initial approach. Functions. These return something called an IO. It just means that they perform some side effects. Maybe they query a database. Maybe they talk to an external service. Doesn't matter. And at the top level, you look at this diagram. You take these functions, which each abstracts a certain step, and you compose them together. However, there's a problem here. There's a small problem. This type of viewing the system, this logical diagram, does not lend itself to a straightforward translation with function composition, because you have stuff that gets a little bit weird. You have splits, like for example here. You have merges, like for example here, and more complicated, you have feedback loops, like stuff like this route here. It gets pretty difficult to code things like this with with your everyday function composition. So instead, at the top level of the program, at the top level of the processor, to assemble these things, we went a different route. We went with stream, and we leverage the capabilities of the Akka streams library. Instead of abstracting our steps as functions, we abstract them as stream components. This is an object representing a stream component, marking a step inside our payment processor. These components These steps, we view them as simple black boxes with input and output ports. 0 or many input ports, 0 or many output ports. Doesn't matter. These ports are linked together through the graph DSL. This is what we get for free from Akka Streams, and it would look something like this. As just to link these three components together, it would look something like this. Akka protects us against a very important class of errors, type errors, because the type that you have for the output must match the type that you have from the input. So if during fraud detection you expect a parsed transaction, you can make sure that the output from the parsed matches the input expected in fraud detection. Yeah, once you have all of these kinds of components assembled together, what you get is a large graph, a large streaming graph where messages are passed asynchronously from component to component until the entire job is done. Okay, let's get back to some actual code. Our initial logical diagram, which I first showed you how we would code as functions, let's see how it looks if we code it as a stream. And this is what it would look like. There are some advantages here that really jump out. First of all, the code for assembling this stuff is really short. It fits into a quarter of a PowerPoint slide. Then, it's very intuitive. There's a one-to-one mapping between the drawing that I did on the bottom and the code I wrote here on the top. Transaction source goes into parsing. Then we have a merge here. I didn't draw the merge, but there's a merge here in between, which goes inside fraud detection. Fraud detection has two outputs, one of them that goes to the reject and one of them that goes to working hour verification, and so on and so forth. Every arrow from the drawing here gets translated to this tilde arrow operator that we get from graph DSL. And again, this is actual demo code I wrote to express this processor at the bottom. But it's not that simple. I only drew the happy path over here. So far so good. This thing already made our lives easier, but we need to add a complication to handle something. We need to handle errors. I haven't talked about error handling yet. Errors appear. They appear spontaneously and they appear within these components. Not all transactions are going to go through the happy path, and you need to account for this. So we need to assume that everything along the way can fail. Not only that, there are classes of errors. There are classes of failures. Some failures happen because of a temporary shutdown of a database, for example. Maybe your database was down while you were trying to query it. For the exact 2 seconds that you were trying to hit the database was down. That's not that bad. You could theoretically retry processing the transaction, and during the second or third run, it could potentially go through. However, there are classes of errors where there's literally nothing you can do. For example, if parsing failed, if between this thing and this thing, you had a failure here where you could not parse the string you received to an XML format, to a schema definition, there's really nothing you can do about it. The failure is going to keep on failing no matter how many times you retry. So we differentiate between errors that we can retry and errors that we cannot retry. And we can do this by design. And here's what it would look like. It's a bit more complicated. It's a bit more involved. Between the drawing I had previously with the happy path with only green components, I now added these red components over here to model the error flow. And what did I do here? Well, every component has an output with a red line signifying any error that happens within these components. So anything that goes wrong within any of these simply sends an error through this flow where they are merged together in what we call the error flow. They go through a login notification step and they go through a verification where we basically interpret their type. We look at the type of error that we received and we put it in one class, either retryable or not. If they are not retryable, if there's nothing we can do about them, we simply store the error and then move it back to the normal path. We delete it from the input and we push it to the end of the entire flow. However, if we figure out that it's a retryable error, that we could potentially simply retry processing the transaction, maybe like the database was down for 2 seconds or something, we do something else. We don't put it on the main flow and we don't delete it from the input. We leave the transaction here in the transaction source and we simply just push this thing to an error sink, which is probably a log of retriable error, which is like a log of retriable errors. But we did not delete it from the input. And because we did not delete the transaction from the input in this case, we are free to process it again. We are free to send it again through the entire flow and actually retry the whole process again. This is actually very interesting, and you can, this way we guarantee error handling by design from every component, and we interpret them in their appropriate class. Okay, how this looks like in practice is something like this. It's something like this, where it's a bit more complicated than the initial flow, but it's still readable. It's still humanly readable. Only in this case, it's a half of a PowerPoint, not a quarter of a PowerPoint. Now, some general notes I want to give before I wrap things up. Again, our main unit of abstraction is the flow component, where we write pure functional code. A lot of times we have to decide what we model with pure functional code and what we do with components. And we're getting better and better at making these decisions, but it's not always immediately obvious. Then components can be arbitrarily complex. They can query databases, external services, or very interestingly, some of them actually model finite state machines. Like, for example, if you want to ensure you only do processing once, we have an internal state machine inside the appropriate component where we make sure once a transaction hits processing, it cannot hit processing again. So we protect ourselves against duplication of processing with this internal finite state machine. Like I said in the previous slide, we allow transactions to be replayed in case of retriable errors, but this introduces a constraint. Our components must be idempotent, and we need to be careful how we code them. Back pressure is a big one that we get for free outside Akka streams. Akka streams complies with the reactive streams. So if a component gets filled up, if its buffer gets filled up, it can notify things backward and make sure that it doesn't get a buffer overflow. And we get horizontal scalability by using Akka cluster with sharding. Now, before I wrap things up, I'm going to jump over a few things because I'm a bit pressed for time. And I'm going to give some generalities on how we chose the ecosystem. So what you can build with it, we build processing, we build transaction processing engines with it. We have great platform and library support with Akka streams and the CATS type level and the type level ecosystem. It fits very well with our problem domain, where we map the logic of processing transactions to a stream, to a stream graph. And the last two are the most important probably for me. We get a lot of correctness guarantees by design due to the language and the libraries that we use. The type system inside Scala is very, very rich, and it protects you against a lot of errors. It's a bit difficult at start to understand all of the subtleties, but once you get the hang of it, you understand how protected you are at compile time. Very importantly, at compile time, the compiler rejects your code unless you get it really right. So it has a lot of correctness guarantees. And last but not least, even after 6 or 7 years already of doing this stuff, the language still finds ways to surprise you and gives you aha moments of joy when you get stuff right. So it's actually pretty fun. And that's it from our side. I look forward to your questions. We are Vesper. Yes, we're also hiring if what we talked about seems interesting. This is our email addresses. And yeah, ING has a contest given that we're one of the main participants in the conference, and I left here some notes on what you need to do to join, to participate in the contest. And that was it from my side. Let me see. Yeah, I think we still have a couple of minutes. Right, it's not actually 12 o'clock yet.
Of minutes necessary for a few questions. Thank you very much, Alexandru. Thank you very much, Mihai. Questions, if there are from the audience, they will come on the Q&A section. Sorry for mumbling. We are waiting for them. If they will come after your speech, then we will for sure ask you to answer offline. Until then, please, one question for me. You mentioned about streams. How do you test them?
Right. So it's a long discussion, but I'm going to say something that I find really interesting on how we do the testing. Normally, when you run a stream, the stream only performs side effects, so it only moves transactions from one part of another. But there's another way of running them. If you're interested, for example, in transactions collected in a certain queue or transaction processed through a certain flow step or whatever, you use what we have. You use the so-called materialized values. Like Akka has this feature that you can run a stream and the actual running of the stream gives you back a result. And that's how you test it. You look at the result of running that stream. And maybe you want to do a unit test and you don't have, you cannot actually hit a SQL database. You can mock that. You can mock it and have an in-memory database for the components, for the stuff that you don't really have access to for a unit test. Run the stream and force it to give you back a value. Like normally it wouldn't, but in case of testing, you want to get back a value and you want to get back like what transactions did you actually process or what transactions failed. And that's how that's how I find it very interesting to run it and get back results. That's how you would test it.
I would add that the streaming part is plumbing, wiring, right? So you first test the individual components, which is the more important part, and maybe you test the business logic there, and then stream tests tends to be integration tests, even if we use mocks. So you start with the unit tests, let's say.
Yeah, there's a layered approach to it. There's incremental approach to it.
As always, incremental approaches work better nowadays.